Hello, welcome everyone to the second session in this morning. The first talk that we are going to have is going to be by Kurt Stirewalt, who is currently the Vice President of Knowledge Engineering at RelationalAI. For many of us who at some point were doubting between academia or industry, here we have an example of a person who has done it all. He, after his PhD in the Georgia Institute of Technology, he was a researcher and then tenure professor at Michigan State University for 11 years. And then he's been in several software development production teams, places like LogicBlocks, Infor, and RelationalAI, where he's been produced and also managed the development of several products for companies in sectors like telecommunications and finance and even retail. So today, he's going to be talking about the method for scalable modeling and of relational knowledge graphs. So without further ado.
Thank you. All right, thank you. And thank you for the invitation to speak here. This is, it's been a good workshop so far. I've learned a lot, and I'm going to talk about something today that is a little different, as he suggested. Let me just kind of jump into it. So I'm going to cover a problem space that I think should concern this audience. It's applications built around knowledge graphs. And built in a style where the knowledge graph really encapsulates all the knowledge so that the applications get easier to write. That's kind of the punchline. I think we should all be concerned about this. This is, I think it's obvious that if you have knowledge graphs, that helps with many AI tasks, and indeed that you can often use AI in helping to construct the knowledge graph. I'm going to take that for granted. I am going to, however, focus on some concerns that are concerns of an audience who is not us. All right, these are the people who actually, customers who would actually go declare this knowledge and try to build these knowledge graphs. They tend not to be PhDs. They tend to not have, they may not even have backgrounds in computer science. And so a lot of the concerns that I'm going to be focusing on are concerns that come up when that audience actually tries to apply these approaches. I'm going to offer some proof points, but not proofs. So the proof points are examples of how we've applied this in practice and kind of what we've learned from it. And I'm going to provide some reflections on having applied a formal language for declaring these knowledge graphs, the one we use at RelationalAI, which is based on data log. But I'm not going to give a new formal language. I'm not going to have results and expressivity. I will have some, I'll touch on some topics that get to design of languages for simplifying some of these concerns and things like query rewriting and many of the kind of problems that were discussed earlier, but in a much more applied setting, much less theoretical setting. All right. So I hope you find it interesting. Let me jump right in. The context here that we're looking at is building what we call applications in a data or knowledge-centric enterprise architecture, and what makes the space of solutions interesting is that they are based on you have applications designed around a central knowledge graph, right? There's an emphasis on conceptual modeling and semantics. There's an emphasis on pushing knowledge into the graph, as opposed to having it implemented possibly many different times in applications within an enterprise. And it's been shown, and our results actually back this up, that when you build solutions using this approach, you get some pretty dramatic reductions in code size. I'll show you some examples here in a moment. It lowers development and maintenance cost. It's kind of all goodness. Okay, it's a very good paradigm. The proof points I'm going to show you are using relational knowledge graphs. And so the ways in which we've done this to date, I've been doing this now, I guess, about 17 years. At a previous company to RelationalAI and also at RelationalAI, we built a number of these. One example is in fraud detection and natural language querying of a big enterprise knowledge graph in a telecom context. We did this with colleagues at RelationalAI, including some folks who are in the audience here who help with this. Another proof point is securities analysis for tax and audit, which is a quite different application of the same idea, but it's also in this space. And previously at LogicBlocks, we did a lot of work in planning and supply chain management and retail, where we're using knowledge graphs. We didn't call them knowledge graphs then, but that was basically what we were building. We were building solutions in this style. And so a lot of the reflections will come from that as well. Okay? All right, so the first proof point, this came from work we did over the course of a couple of years with a major telecom provider in the US, AT&T. And what they were interested in doing, they had a number of business use cases. One of them was fraud detection. They had an outrageous amount of fraud, particularly of devices that they would sell in their stores. If you buy an iPhone, there are many different ways that fraudsters can kind of trick the system into getting that iPhone for free, believe it or not. And they were tricky to discover, tricky to root out. And so they used an enterprise semantic model that we helped them build to find instances of this fraud and actually to prove to store managers that some of their employees were committing this fraud so that they could take action on it. So that's one use case. Another use case was natural language querying by what they call citizen data consumers. So we built this big knowledge graph that links together all this information from many different silos at the company, and now business users can then actually ask questions about it in natural language, and those queries will get turned into queries that will get executed against the knowledge graph to give answers. Okay. I'm actually on that one. I won't say too much more about that particular application, but I am including over there on the right a paper that's due to the work from some colleagues, in particular Christina Savili and Evgeny Sharkonov, who collaborated in that work. And they were using an off-the-shelf LLM without fine-tuning to actually do this. It's kind of an interesting result. Okay, so this particular enterprise knowledge graph, it was big. Okay, it consumed and indexed into terabytes of customer data across 20 different sources from 4 different data silos, business units. And when I say data silos, I really mean that these guys didn't talk to each other at all, right? They had, every one of these business units had their own IT systems, they had their own data scientists, they had everything, but they didn't really share. They couldn't really share until they built this big knowledge graph. And the key artifact of this knowledge graph was something called the One AT&T ontology. It was a conceptual model of their whole enterprise that actually allowed these different data sources to be integrated so that they get these benefits. Okay? So on this proof point, kind of a few metrics I can give you. The model that was built had, I can't give precise details because they don't want precise details to be shared, but it was greater than 500 concepts that were in that were being modeled in the graph, over 1,000 relationships, and crucially, over 2,100 different rules. Okay, and that seems like a lot. If you've ever built a data log-based system, it's probably hard to grok having 2,100 rules. That's a lot of rules to maintain. And it was about 20,000 lines of code total, if you just did a code count. All right, so that was one proof point. This went into production and did provide business value in the ways I'm suggesting. One other thing it did, by the way, is I mentioned here this business use case of amortizing data engineering effort over many projects. One of the big benefits of it in the end was that there was now one place where all this data engineering that had to be done to build the knowledge graph in the first place was done and could be reused. If you've seen data science projects at many big companies, you'll notice that there's often not a lot of data science. There's mostly data engineering for the first 3 or 4 months, and then a small amount of data science to get a result. Right, so that's another problem that this addressed. Okay, another proof point involved reasoning about really complex business rules. This was at a tax and audit firm in the United States. And the particular example here was securities analysis for tax and finance. So securities analysis means if I've got a hedge fund or a mutual fund, they're buying and selling stocks, and there are any number of different tax laws that constrain how those purchases and sales need to be taxed. There's a lot of business logic that goes into that to be modeled. They had a solution that was over 800,000 lines of C#. I can't tell you how much SQL. It was a bunch. And that solution had been in production for years, but it had trouble processing very large quant funds, funds from hedge funds that were doing quant trading, rapid fire trading. So we actually gave them a solution. At the time I reported this a few years ago, it was I think it was around 20,000 lines of code, 20,000 lines of declarative modeling code versus again 800,000 lines of C#, and the large we were able to process these large legacy these large quant funds without running out of memory, which is what the legacy solution did. What's interesting about this one is, so first, it's grown quite a bit since I reported that result a couple of years ago. It's now almost double because a lot more features have been added to it. It's about 50,000 lines of REL, the language that that we use to program the to declare these big knowledge graphs. A significant amount of this graph is actually derived. So unlike the previous example with the telecom provider, where the knowledge graph is essentially indexing into their data and giving them the ability to navigate over this. In this example, most of the knowledge graph was doing heavy computations and deriving synthetic concepts. They were basically modeling what an accountant would do on a daily basis to try to work out, how these different funds need to match and how these different trades need to match for purposes of taxation. Okay. Yeah, so the benefits that we got, in addition to the size reduction, there were a lower number of defects, just because there were fewer places for the bugs to hide, with only 50,000 lines versus 800,000, and a much smaller dev team could be used to maintain it. Okay, so tangible benefits, a very, very happy customer there. Some things that are common in these two proof points is the use of models to capture a business domain. So you see things like here on the right. Just use you see this. I'll show some more examples of this in a moment. But both of these customers used these conceptual modeling notations to kind of capture and codify their business domain, and then they codified their business rules in the form of rules. Okay, that looked roughly like this, and they were rules that were small enough and verbalizable enough that actual business users could validate them and say, yeah, you got it, right? This is exactly what we do when we're analyzing this particular tax use case. This idea of verbalizing a model in English is a big deal, right? Domain experts can validate these things correctly or directly so that you've got it correct, and it changes the nature, really the whole way you write code and write tests. Okay, so there are a lot of benefits to having done this. I mentioned a couple of them, right? So, and actually Mahmoud suggested in his talk earlier, one of the things you get by pushing your computation into a knowledge graph into the database is you don't have to move big data out of the database to go do some work and then push it back. We're also, as I mentioned, we're able to leverage and contribute to an enterprise semantic layer so they could kind of amortize the work to build this over many different projects. A massive amount of code reduction we saw in the tax case, and as I mentioned, kind of a change in emphasis from programming a solution to modeling a domain. So it's all good, right? And we can go home? Well, sadly, no. So it was successful. We got it working, but I think as many of my colleagues here can attest, it was a lot of work to get these things working. And some of that work we found got harder as the models themselves got larger. So the key problem that I want to spend the rest of of this presentation talking about is how we manage these models as they grow larger, how we manage these problems of scale. And I don't mean data scale here. I mean the model itself as it starts getting larger and larger. It starts having scalability problems of its own. All right, so so there are a couple of 2 or 3 different reasons why this gets harder. One is this first problem, right? That if I have a clean conceptual model of my domain when I begin, it often degrades. And it degrades for a number of reasons. One is that, as I showed you that diagram earlier, often it's customers will be able to quickly put together a clean conceptual model of their domain. but that model's not executable, right? And so because it's not executable, it starts to, the actual rule, the data log rules that you write to implement it start to drift from the original model, and eventually it becomes kind of a useless artifact. It's also the case that many of the constraints, the domain constraints that you identify and can model very cleanly, conceptually, they're often implemented kind of implicitly in rules rather than declared explicitly and then used. So that makes them unavailable for things like performance optimizations, and therefore that means then the writers of the rules have to do performance optimization by tweaking their rules and reformulating them and introducing intermediate results that may have poor names, et cetera. So these models just get ugly and difficult to maintain over time. Also, as more of the application logic kind of goes into the graph, the number of rules that you need to maintain grows quickly, as does the complexity of your joins, as does the number of indexes that have to be created because you're having different data access paths being used in more cases. And just generally, as these models grow in complexity, the developer time shifts from modeling and declaring rules to reformulating those rules to improve performance and doing things that programmers find hard, right? Like coming up with good names for good names for things and keeping them readable. Okay, so just trust me on this, that as these things grow, they get harder. Now, we've known about this for a while, and so we've been looking for ways to make the modeling process more scalable. And there are several things you can do. One is to incentivize and reward good conceptual modeling. And I'll spend a little bit of time showing how we're doing that with a new Python package that we've built for allowing users of our relational knowledge graph management system to build their solutions. We can also do some things with code generation, right? We can, we've done some analysis of what kinds of tasks most of the rules are doing. Many of those can be automated. Okay, one is in model population, and the other is in this thing called multidimensional measure aggregation. So I'll talk about both of those. Okay. All right, just to kind of jump in. So the first talk about how we are going to incentivize and reward our users for doing good conceptual modeling. And so we're starting with models that look like this, right? This is where we've had good success with customers in doing modeling. They built these graphical models that have this kind of look. This is in the object role modeling notation. I don't know if you've seen it before, but it's a nice graphical, verbalizable modeling notation that, as you can see, nicely captures the main concepts and relationships in a domain, as well as constraints, domain constraints that you can expect and you can therefore use when you're building a knowledge graph. And it's got a lot of neat things here. I'll just point out a couple. So first off, you'll see there are major concepts here like subscription and account. It's the kind of thing you can imagine, a wireless telecom provider. They've got subscriptions that their customers have. You can have multiple subscriptions per account. You have subscriber phone numbers with subscriptions. These things here are relationships, right, between that connect the concepts. All these things in purple are domain constraints, and you can see they're quite rich. This is typical when you actually do a good conceptual model of a domain. You actually get quite a bit of this information. Like, so this one here says that a phone number, okay, which is a concept, has to be in this range, right? Or at least in the United States. Right? That's the range of valid phone numbers. And so if I ever see in my data something that purports to be a phone number and it is not in this range, then the constraint's not valid. And I shouldn't treat it as a phone number. Okay. Some of these other constraints, things like this says that the timestamp when I start billing at a new monthly rate has to be less than the timestamp when the account terminated. Okay, there's a lot of this kind of stuff that you can quickly find either immediately when you're starting to work with a client or over time as you start to learn more about their business. And you get these very rich constraints that you can reason about. One other one really quickly, when you see these lines here, these little horizontal purple lines, these are uniqueness constraints. They're saying that within a relationship like this one, these first two roles here have to be unique, It means that it's essentially establishing a functional dependency, saying if I have a date and a device, that gives me a unique subscription, okay, that purchased that device on that date. Right? And you can see I can have multiple uniqueness constraints over different subsets of these roles. This is quite common. Okay, and this is quite useful information to know when you're optimizing queries and you're trying to build these things at scale. Make sense? Okay, so we have these things. One more quick thing. So notice that these in these relationships you can verbalize them in either direction. So this little text here tells me how to verbalize facts in this relationship. I can verbalize them either by saying a subscription is part of an account, or I could verbalize it in the reverse direction by saying an account comprises subscriptions. Okay, so we have support for English language verbalization built into how we declare these models, which is actually quite useful when you're trying to use generative AI to help you either query your knowledge graph or even to help you build it. Okay, so how do we declare this in RaiPython? You can see we have a little syntax here. I'm including all the little colors here because when you're using the RaiPython package and you're declaring your model textually, you get this nice feedback. It's nice and blue if it's an object that's been defined before. Right? So when I have a concept like phone number in this constraint, I can declare it. I say phone number equals, it's a concept, its name is phone number, it extends in this case an integer, and I can define this constraint here to capture this piece here. Okay? I've said that once and done. You can imagine I might have 30 different data sources that have phone numbers, and I might have 100 applications that use phone numbers. They're all going to need to check this constraint, but now I can just declare it in one place. Here's an example of an entity type, like account, that has what's called a simple reference scheme. So entities, or you think of them as opaque objects that represent objects in the real world, but they all have to be referenced somehow. And that requires having relationships like this one and other concepts sometimes, like account numbers, that tell me how I'm going to reference an account. In this case, I'm saying that an account is identified by this thing called an account number. All right? And there are some constraints here that make very clear that I'm identifying accounts by account number. Okay? This is how you say that this thing in textually in RaiPython. You'll notice that when I declare the relationships like this guy account ID, I'm actually giving the verbalization that I would have declared in the model. So this is available for processing later. It's available for use when I'm querying it. Another thing to note is that these concept objects like account number and account here, okay, that I'm creating and I'm going to be using in building this model, they act like containers for the relationships that in which they play a role, in which those concepts play a role. That's actually important because as these models grow, one of the scalability problems is if you've got thousands of relationships, how are you going to remember their names, right? They're just going to be hard to find. So one way that our customers have found to do this is to group them by the concept that plays the first role. And you can actually use that in IDEs to help you kind of figure out which of the relationships that are available I might want to use in a particular role. Finally, this guy here, this identified by, this piece here allows me to kind of capture all these tricky constraints in a nice, convenient way. Okay, and declare them once. All right, I'm going to have to speed up just a little bit for time, but you can see how this is a more interesting example because I have subscription here, which has a what's called a compound reference scheme. I need to actually, if I'm going to refer to subscriptions, I need to refer to them both by an account and a phone number in order to uniquely refer to a particular subscription, right? So you would imagine if I see this in some table somewhere, I'm going to need at least 2 columns in order to identify the subscriptions. And I can capture all the details that are in the diagram. I can capture them textually. Okay. I can also capture these trickier constraints, like I showed you this example where I've got a ternary relationship here, and there are multiple uniqueness constraints that allow me to say that there are multiple functional dependencies in this relationship from the different roles of the relationship to their values. And I can capture all that. Also, all this code, everything I've written here, I could write by hand, Or if it's something where I already have a one of these ORM models that I've defined, I can derive it automatically. So in fact, most of our customers do that. They actually maintain the ORM models, and when they run their queries, we rapidly convert it through an adapter from this form into this, and then use that. They use that to write rules. Okay. So the kind of benefits you get from this, I can, I have verbalization. If I've literally been typing this in, and then I want to know, hey, what have I said? I can say, so I define this relationship like accounts start billing at. I can say print accounts.startbillingat.verbalize, and I'll get something like this, right? A natural language verbalization of what I've said. If I then add another constraint there, like I say that the account role is mandatory here, that's this little circular constraint there. When I get that in here, the verbalization changes, okay? And this is live, right? So if I've add new constraints, I can make this. This is just another way we're rewarding our customers for building and maintaining a good conceptual model. We're giving them a good programmatic way to do this. This is not something we had before we built this Python package. All right, you've also seen a little bit of this, but we can declare rules in Python. So some relationships are going to be derived, like last subscription date for an account. It's basically saying, you can imagine this would need to be derived through some kind of aggregation, right? And you can express aggregations this way, right? You saw Marcelo showed a little example of a where define rule yesterday. This is a little bit more complicated because it's got an aggregation in it, but you can see how kind of how it works. I'm basically saying here that an account has some last subscription date DT if that DT is the maximum date where these things occurred, right? A subscription was purchased on a subscription purchased a device on some date, and it's part of an account, and I'm grouping by account. Okay, you don't have to worry too much about the syntax. We just it's well formed. Okay. All right. Other benefits: the IDE support for managing large models, as I can catch typos quickly in the way most Python programmers would expect. So, for example, if I'm typing along a rule and I see that this doesn't turn blue like I expect, and like people who use IDEs expect as they're typing along, they'll know immediately, hey, there's a typo here, and they go fix it. If they are writing a rule and they say something, they can search for the relationships that they're looking to define, because as soon as they type account dot, they'll get a little drop down here that lists the relationships that we defined before. So little things like that, right? Auto completion. Also, because we've defined these models so that they're verbalizable and so the relationships can verbalize in either direction or in multiple directions, you'll notice that remember I said at the beginning that account.comprises is the same as subscription.is part of. Right? So if I start from account, I see comprises. If I start from subscription, I see as part of. It's the same relationship, but it's a much nicer, more convenient way to access it. Okay, hopefully that makes sense, right? This is just kind of a general way of allowing customers to create these models and maintain them. All right. Now we've done some other things too. Once we've got that capability in there, once we can reason about those models, we can actually start doing more code generation to prevent them from having to write so many rules in the first place. And so the first thing I'm going to show you, just briefly, is this one. When one of the things that we found takes a lot of time by users of our solution in the rules that they write to populate a graph is just actually taking the data and populating the nodes and edges in the graph from those data. In the AT&T use case I showed you, that was about 70% of the code was just in doing that. Okay, and the way it's done is you write rules that derive nodes and facts in your graph from rows in your tables, and the long and the short of it is, if I've got a 50-column table, I'm going to when I load that, I see 50 different relations, one for each column, that maps the row to the value in the column. Okay. And this is tedious, in some cases tricky. It's easy, you can imagine, for customers to write rules that violate constraints, like the phone number constraint I showed you earlier. That's an easy one to violate. Also, the rules that they write might perform very poorly at scale. This is the one Nadia mentioned privately yesterday that some customers have come up with. It's very easy to write rules that do population of the knowledge graph from data that just don't scale very well. And so it's important to automate this for a variety of reasons. One, large enterprise knowledge graphs are going to index into a lot of tables. The status of a table as a source of record might change over time, right? So I might initially have data from some source that isn't authoritative, and later I find the ability to get the authoritative source, and I want to change it. I don't want to have to rewrite all my rules, right? I just want to make a one-line change. You may discover model constraints later that you didn't know before. And just generally, if there are patterns that lead to good performance, rather than asking your customers to learn the patterns and apply them, it's just easier to enforce them. All right, so let's, as a quick example of this, let's suppose we have this model. This is a snippet of the model I showed you earlier with subscriptions and accounts. And we want to populate it from data in these two tables, subscribers and accounts. If we first map data from this accounts table, what we can see is that this accounts number column needs to really basically produce facts, both account nodes, okay, in the graph, but also facts in the account.id relationship, right? That's this this relationship here. Okay, so this is the rule that does it. Pretty small, pretty easy to read, I think. Right, I'm just saying where there's a row in the accounts table that whose number is account number, I'm going to define a new account, a new instance of account, whose ID is that account number. That's pretty readable and pretty verbalizable. I would do the same thing, or I could do the same thing, for this account number column in the subscriptions table, or the subscribers table, right? And it would basically, you see the rule is pretty much the same, it's just I'm referencing a different table. I'm deriving nodes and facts in the same relationship. So having declared those two rules now, I've actually mapped two of these columns in. And if I have a given account.id fact, it might come from some row in this table, one or more rows in this table, or both. Okay, just from the way I've defined it. And that's kind of baked into how the rules are written. All right, so now let's think about how to populate subscription nodes. This one's a little harder. Remember that earlier we said a subscription needs to be identified by an account and a subscriber phone number. So that means we've got these two columns here that we need to map in. But if you think about this one's a little trickier. I need to do these two columns. I need to map the account number value to an account, which means I've got to map it through an account number to get the account. And I need to map phone number, the value in this PHNR column to a phone number. And I need to remember to check the constraint. Okay? So this ends up actually touching a lot of this model just to map these two columns. Here's the rule, right? It's not horrible looking. You could read it and make sense of it. But it is kind of complex, right? You can see it's kind of weaving in, mixing different concerns. You can see how I put in the concern about checking that the phone number is valid here. I have to look up the account from that account number. I got the account number from a row of this table. It needs to be the same row as the one where I'm getting the phone number, etc. Okay? So again, not long. It's not a long rule, but it is one that mixes concerns. And this is the kind of stuff that actually does many of our customers do find tricky. Okay, so there's a lot of accidental detail in these rules. I think I've kind of gone over them. So just at a high level, we want to do something. We basically don't want to have our customers write rules for this. We want them to declare something at a higher level. So we introduced this thing called a binding language. This is very similar to mappings if you're familiar with R2 RML and other knowledge graph contexts. It's kind of similar to that. All right, we're basically just establishing a semantic connection between the facts of one or more relationships and instances of nodes of one or more concepts and the rows of some table. Okay. The syntax here, if I have a column, I can say the column dot binds and then give the roles, or alternatively, I can say a role is bound by one or more columns. Here's an example, right? So the rule we had that went from number here to this little piece, we can declare in this binding. Accounts.number binds to this role, account ID of account number. Okay. And that establishes that connection. What's interesting about this one is because there are constraints on the model that say when this role has a value, it's identifying an instance of a node that plays this role. So in fact, this one binding not only says this, but it also says that. Right? It's also populating. I'm using this to create new instances of this entity through that one binding. Okay. All right. Similarly for subscriptions with phone numbers, if I do the binding there, that would actually generate rules that would check that it would find that this value of phone number doesn't satisfy the declare constraint, and so it would be excluded. That row would be excluded. We don't yet generate error messages for this. We just drop the rows, but you can imagine how we can take that further and also provide feedback. Okay, just quickly, if I look at the, for that example, this is the minimal amount of code I would have to write using these bindings or these mappings to basically tie those tables into, map those tables into a knowledge graph. And I'm doing a lot of reasoning about the declared model to get this minimality and be able to generate good code. Okay? All right, so that's one way we used code generation and from these models to simplify. And again, in examples like the AT&T example, that was like 70% of the rules that one would write are doing that problem. It makes it much, much smaller. We can, again, generate better errors, better warnings, and more performant results from that. So that's a huge win by itself. All right, the next one is another problem that often comes up. These are, I'll try to motivate it here. This is an example from a different client where they have financial transaction data, and they want to report information about those transactions at many different levels. So what this model is showing is I have this concept here called a transaction, a financial transaction. It has some values associated with it by these relationships. A transaction exchanges some amount in local currency. Right, so if I buy 100 shares of IBM, I'm exchanging whatever 100 times the cost is in the local currency. But that same transaction might settle some amount later, possibly in some different currency. If I'm a foreign buyer, for example, they'll convert from dollars to euros. Okay, so I've got these relationships that keep track of the amounts that are associated with this transaction. The transaction also participates in relationships. For example, it trades in some asset, right? The asset here would be IBM in my little example. It's enacted by some entity like a hedge fund, right? Those entities might themselves be owned or controlled by other entities, which makes this interesting. And these things might roll up further. An entity is located in a region, an asset is listed on an exchange. I might want to look at this information like these local amounts. I might want to look at them at any of these levels of aggregation, and there could be multiple of them. So I might say, let me understand the local amount aggregated to the asset level. That would group together all transactions related to IBM, for example, and show me what their total cost was in local amount. I might ask for the local amount aggregated to the exchange entity level, or any combination of these. Okay, so a simple example. I'm calling these measures, by the way. These amounts that I might want to group and aggregate by navigating paths in the graph. They're called measures. So one measure that someone might ask is sum up the transaction local amounts per asset. If I had a graph that looks like the one on the left, I would imagine going, from transactions and these amounts, mapping them, looking for paths in the graph to get up to the assets, grouping those values that propagate along those paths, and summing them up. I'd get a table like the one here, where I've got asset and local amount, okay, aggregated. This is what the RaiPython rule would look like. Again, fairly straightforward. It's using aggregations, not super complicated. Now let's look at another one. So now we want to sum up transaction local amounts per entity. Now this one's interesting because if you look at an example graph, I've got the same transactions. They might map, maybe the first two map to entity E1. The second, T3 and T4 are enacted by entity E2. But entity E1 is actually owned by entity E2. So this makes this one a little ambiguous. What do you mean? Do you mean to only measure transactions that are enacted directly by some entity, or directly or indirectly, right? You can actually get multiple examples here. These are the two possible answers, depending on whether or not we traverse these edges as well. Okay, so if I look at one of these measures, here's the rule, fairly straightforward. That's the one that just derives using paths to an entity node that directly enacts transactions. This one is interesting. If I want to also include the indirects, now I've got two rules. These two rules derive into the same relation here, okay? This one is recursive, okay? Because I need to, it's referring to the local amount for an entity that I computed via a previous, a prefix of the path that I now need to further aggregate, okay? So won't drag you through the details, but you can imagine if we've got path queries that involve arbitrary linked path, they're going to be recursive. These are exactly the kind of rules that are tricky for many of our modelers to write, and they get even trickier if I want to have multiple dimensions of aggregation, like I wanted to group by asset and entity, and I wanted the entities to be direct or indirect. You can imagine how these the rules that you would have to write if you wanted to write them by hand would have to think about a lot of these interleaved cases and get very complicated. All right, so what we do, this is tricky enough that we invented a specialized way to declare these. We call them derived measure expressions, and they're basically just ways of saying, hey, I want to tell you an aggregation method, I want to tell you this base measure that I want to aggregate, and I want to give you some path expressions, possibly multiple path expressions, that will tell me how to do this aggregation. And by analyzing this and by reasoning about the constraints that are declared in the model, I'm going to basically then generate exactly the kind of logic that I showed you a moment ago that was written by hand. Okay, this accounts for quite a bit of. So here's an example. Those two rules that I showed a moment ago would reduce to something like this, which I think is pretty readable in terms of trying to for people trying to understand this if they're trying to report and reason about the data in their graph. Notice that we do things here like there's a cleany star operator here, right? So these I can say 0 or more occurrences. These are basically they look like little regular expressions, limited regular expressions over strings, where the symbols in the strings are roles, right? That I had in the model, right? So we use roles already in several ways. They're declarable in IPython. We use them when declaring these mappings or these bindings. We use roles. We're also using them here. So once your customers are used to using this and they're in their model, all of these ways we're providing extra value for doing code generation and reducing the amount of rules they have to write are all using the same thing. Okay? Okie doke. So there are many other examples, but hopefully I've given you a bit of a flavor for how what we've developed with IPython is able to help customers deal with this model scalability problem. Just to kind of summarize it up, I've shown a couple of proof points that I think demonstrated the value of these large relational knowledge graphs in practice. We've shown the technology scales, even though, again, some of my colleagues will remember it was hard going sometimes, but it does scale, and it does provide value to customers in many different domains. Okay, I think I've given you examples of 3. But I don't think it's limited to those. Delivery does get more challenging as the models that you declare grow. And the lesson learned, honestly, is that many of the modeling tasks really shouldn't be declared using rules. We need to invent higher level abstractions that then generate the rules down from those higher level abstractions. And I think that's actually consistent with the kind of things Mahmoud was saying earlier today, right? That if you want to, for example, do gradient descent on, without unpacking your data and having to rediscover things that are there, you have to do code generation of some form to do it. We're saying the same thing here, just in a different context. So this IPython package it's not yet generally available. We're hoping to make it generally available by the end of September, I think. But it's the kind of thing you could start playing with. It directly supports conceptual modeling and rule declaration with a small number of constructs. And I think I've explained how and why it incentivizes modeling. We also have these libraries built on top that take advantage of the fact that we have a nice Pythonic way of building up these rules that allow you to build these higher level abstractions, like the ones for binding and for measure aggregation. Okay. All right. Future work. We want to continue to leverage constraints that are declared in the model in several ways. So for example, if I have uniqueness, mandatory, and exclusion constraints, I can actually use these to inform query optimizers to, or actually the database system itself to use more efficient data structures. I can do things like optimize queries that have outer join semantics, but because you know things about mandatory constraints, you can actually prevent a lot of the additional cruft you need to generate in order to implement the outer joins. You can do better type checking of your rules if you can reason about exclusion constraints. There's a lot more we can do here. We can also, this is a topic that I think is going to be discussed after this workshop. There are a lot of policies you might want to automate for discharging constraints in the model. All right, so those models I showed you had a lot of rich domain constraints in them, everything that was in purple. You would want those constraints to be somehow discharged. All right, if you went to the trouble of declaring them, you certainly expect they're going to be enforced, or at least you're not doing it in vain, right? And then your data don't behave that way. Unfortunately, those constraints are generally very expensive to check at runtime. If you saw how many of them there were, if I had to check every one of those constraints on every transaction, I'd be spending more time checking constraints than I would actually computing any interesting query. So this is a real dilemma. What's interesting about it is that a lot of these constraints can be statically discharged by reasoning. Right? So for example, if I have any knowledge about integrity constraints that are provided by the underlying data management system, right, by Snowflake, for example, or your SQL database system, then I can actually use those in kind of an assume guarantee style of reasoning. I can use the physical constraints that are guaranteed by the data management system to statically discharge these semantic constraints that are in these models. And a lot of them can go away that way if you have good metadata from your tables. There's also ways that you can check constraints once at the physical level, and then only periodically check them again. A good example of this is, suppose I declare that I've got a relationship, and I declare there's a uniqueness constraint that says there's a functional dependency, right? And I load 10 terabytes of data, okay, and it isn't violated. The chances that tomorrow some new transaction is going to come in that violates it are pretty small, right? Now, they're not zero, so I can't totally ignore it. But if I've actually validated these things once on a massive amount of data, I can probably expect that over time, the systems that produce that are going to behave similarly, and I can just recheck it periodically. I can also do things like turn hard constraints into soft constraints that materialize violators, and then let me check them periodically, or let them raise warnings. Right? There's a lot of opportunities here. The bottom line is this problem of automating policies that discharge constraints in the model is an area of future work. Some open problems that I'll leave you with. One is that a nut that we haven't yet cracked is how we better support rule sets that are inherently complex. This actually comes up in that financial application that I described earlier, where you have a bunch of recursively interdependent relationships in a big recursive cycle. The rules for that, we got them to work, but they don't really look much like domain rules anymore, and they're hard to tune, and they're kind of trouble to maintain. So this is again, we haven't solved this yet, but what we're thinking is that the actual implementation rules, the rules that are delivered, should themselves be synthesized, generated by composing higher level separable concerns. Maybe those are represented as rules, maybe those are represented as constraints or sets of constraints, and we do the reasoning to figure out how to turn those into rules. But that's the thing we're looking at now, and it's an open question to date. And finally, of course, we want to automatically verbalize the rules that are written in English, right? So use generative AI, for example, to speak back what I just typed into a rule to make sure I got it right. We may have a variant of this for rules that are generated via the abstractions we were talking about versus the rules that are handwritten. But this is another area of work to make this even more usable. All right, and that's it. Thank you for your time.
Thank you very much. So we'll open it now for questions. And I can see there's already one.
So thank you for the talk. I have many questions. Some of them we'll talk afterwards, but there is this this language of bindings that you have presented, and I have some questions around that. One of your concerns was to help users not to make mistakes.
Right.
And I'm wondering if you considered the problem of consistency in the sense that, well, someone is mapping an attribute from your relational database to your RM model, and in the relation database, you know that you have the constraint that the value has to be between 0 and 10, and in your RM, you say, well, between 10 and 20. Which obviously gives you a problem of consistency. I mean, the mapping will create problematic transformation.
Yep. Like this one here, right? This is an example where
Yes.
I've declared a concept like phone number. There's a constraint that you want every phone number to have, and you want to check it.
And so, have you? I mean, but this is a very simple type of constraint.
Yeah.
There might be much more complex situations. And have you considered testing consistency of this mapping defined by the bindings in order to provide feedback to users that, hey, you're doing
statically
something wrong?
to say that this will never work. I see what you mean. Yeah. So yeah, the work to date has not been yet to say we've discovered that the well, that's not completely true. So as a general rule, we're not doing a general reasoning about all the constraints one might declare in these models to decide if when I bind a particular column and that I know that it's going to be empty, that it'll drop every row, right? We are, however, what we're doing instead is generating logic to check when we in the rules that do the ingestion that the hold, right? So we'll know that we don't populate the knowledge graph with bad facts, but we may not populate it at all, right? Because we haven't done that check. We do a limited amount of checking, however, if we have physical metadata available. For example, if I know that a column or set of columns is a primary key, that will let me actually discharge constraints. And if I don't know that, if I can't validate that, that means those constraints will need to then be checked. Now, at the moment, we're not generating the code to check them, but they can be marked so that you know that's an issue, and you could fix it either by giving some additional information.
Okay,
And
fair
that's the
enough.
extent of it.
Another question. One of the concerns at the very beginning of your presentation was evolution of the model.
Model evolution, yeah.
Right, and I'm wondering to what extent you could handle it also with the binding language that tells you how one model is evolving into another model, and what you could do with those kind of bindings, those kind of rules, you know, to help yourself.
Yeah, I haven't
evolution.
thought about using bindings, for example, to help with model evolution particularly, but we are, they can be attributed. Bindings, because they're objects that can be attributed with additional information. One kind of information you can attribute them with is this binding from a source of record, right? Which means I could then use that to judge when I'm generating rules, do I actually create facts or do I just reference them? It changes the character of the rules. So in that sense, we're doing some reasoning, but there may be other model evolution problems that, I mean, we do check, we're reasoning about constraints of the model as it's declared at the moment when we're generating the code. But I haven't thought about using them to think about how version 1 of a model, when it evolves to version 2, what might be there. That might be an interesting area to look at.
All right, a question.
Yeah, I have a question. Considering the performance of a system, of an enterprise application designed and implemented with this technology,
Yeah.
versus one implemented with a DB, relational or non-relational DB, plus application code, assuming that both are well designed and were implemented, which for legacy applications is often another assumption to do, but let's make that assumption.
You asked me to try to compare applications designed in this general paradigm versus in the classical paradigm for performance.
Yeah, for
Yeah.
performance, given the both are well
Given that both
designed.
are well designed, yeah.
Which is another assumption.
Good question. Yeah, right. Yeah, it's another assumption. I don't have any direct way to compare that. What I can say is the applications that I think this technology works really well in are ones where, for example, we're trying to invest in an enterprise knowledge graph that we're gonna then query to find, like the natural language querying example is a good one. I would not use this technology to build a transactional application, right? But I'm afraid I don't have between those two extremes. I just don't have any data to report.
Okay, thank you very much for the answer.
Yep.
All right. Is there any additional question? Oh.
I'm allowed. Thank you. Thank you for your talk, Kurt. So I was wondering about this technology from the perspective of the query optimization, because the way it's written now, it's first of all, it's very structured way, right? The whole program is written.
Right.
And you are translating this high-level code into some kind of SQL data log, some kind of database language, right?
Yep.
So is there an opportunity there to take into account the entire program, right? The views and the schema in order to generate optimized queries, right?
Yeah. So I believe there is. The way we've done the work to date is we reason about what's declared in the model. We're not reasoning at all yet about the data, right, or the shape of the actual data. But we do, for example, reason about constraints that are declared to generate rules that should perform better. And we could, in theory, send that information down to the query optimizer as well, so that it could, like functional dependencies and mandatory constraints are good examples of things that you could really use well in a query optimizer. And we could send that information down.
So this would be per query level, right? So for each query, you can annotate with some useful information. What about seeing the whole program as the whole, right? If I see many queries that are constructing the same intermediate sort of join.
Right.
I can create a separate view and make use of it in all other query. I can do some pre-computation because I see that this is popular join.
I see your question. Yeah, we're not looking at that yet. That's a very interesting problem. In theory, if you have, if you can extend something like this that's running, with some runtime recording of past queries, either do an offline analysis to try to decide that. Yeah, it's a very interesting area to look at, but we haven't looked at it yet. Yeah.
Thank you.
Mm-hmm.
I'll ask one question. So first of all, it's very interesting to see that this kind of approaches, logic-based, data log bases, based, that have real-world impact. That's, I think, for people like me, is really, really interesting. So the question is in 2 points. One is actually really linked to what you discussed, and one is more general.
Okay.
So you have this part verbalization, I guess you called it, right?
Mm-hmm. Yep.
So can you do it with, say, old-fashioned, hard-coded techniques, right? Is it really programmed how, from the schema to generate, a nice,
nice verbalizations.
Nice verbalization, or you need LLMs, or what is the role of LLMs?
Yeah.
And in general, is there a role for, I'm trying to sprinkle some LLMs because it's popular nowadays. Would that be useful, I don't know, in other parts, like, for example, building the ontology, the schema, or, in other parts of this framework?
Let me answer the first part first. So one of the virtues of the modeling, the graphical modeling language that we've been kind of adopting and kind of using as a prototype for this is that it was built to support verbalization, not using anything fancy, just kind of pattern-based verbalization. It works really well. In fact, the CEO of our company often uses the verbalizations that are generated from models as an input to ChatGPT to ask questions about the models, and it does a really good job then of answering domain questions. So that part is kind of baked in. The thing that I think is interesting as an application of generative AI for verbalization of a model is with rules. We don't really have any good patterns yet for nicely verbalizing the rules, and there's much more you can say with a rule than with these kind of restricted constraints. So that's a really interesting problem. I think your second question was, can we get these models somehow generated for us, not by modeling them, but by like reasoning about graph or some kind of RAG approaches, for example, to go through documents. That's an interesting problem. I'm not the expert on it. There are people at RelationalAI working on that problem to try to bootstrap a model from textual documents and various forms, but mostly PDFs. And they have some good early results, right? I mean, English, if you've got a system that can process English and you can somehow describe the form that you're trying to generate, they're pretty good. So yeah, I think there's a lot of possibility there. If not for fully automating the model, at least giving you that first cut, right? And then you can extend it. Yeah.
All right. I think we need to move on to the next session. So let's thank Kurt once again.
Yeah.